Let's summarise what we've just talked about. We've talked about carrier distributions. First of all, the density of states, which shows us how many electrons can be present in the material in a particular range of energies. And this is analogous to how many chairs there are in a room. That's the total number of people that can be accommodated in that room. The Fermi function tells us the probability of whether those seats or energy levels are actually occupied. So if the Fermi function is 0, there are no carriers present. If it's 1, the states are completely full. Near the band edge, we looked at the density of states, and it increases parabolically. And this doesn't go on forever. It does close off again at much higher energies, but near the band edge, we have a parabolic variation in density of states. If we know f of v and g of v, we can integrate them to get the total number of electrons or the total number of holes, and we got from that the parameters nv and nc, the effective density of states. The Fermi level can be defined as the energy where the Fermi function is a half. It's also a chemical potential. It tells you the average energy of the carriers, and that will be useful when we start looking at how band structures vary when we change the composition or apply voltages to the material. We looked at equilibrium situations, and in that case the product NP is constant, and in an intrinsic material whose carrier concentration is Ni, then obviously Np is Ni squared. But even if you dope the material, Np is still Ni squared at equilibrium, so if N goes up, P goes down, or vice versa, so that their product remains constant. That product is a function of temperature. And we saw that the conductivity, which is affected by the carrier concentration, will vary with the temperature, and we'll talk more about that later on. Our next topic is going to be carrier action, in which we'll be talking about how electrons and holes respond to electric fields and concentration gradients, and how they can be created and destroyed. And we'll be able to then look at how carrier distributions can vary across a material when we're not anymore at equilibrium.